Okay, good morning, ladies and gentlemen. Welcome to this session. Our first speaker today is Professor Maryna Viazovska from, let me try, École Polytechnique Federal de Lausanne in Switzerland. Professor Viazovska received the Fields Medal in 2022 and is also this year's Frontier of Science Award recipient. The title of her talk is The Sphere Packing Problem. Let's welcome Professor Viazovska.
And now, so now I hope you can hear me better. So as this is how spheres look in the first 3 dimensions. In dimension 1 is just an interval, so packing problem is trivial. In dimension 2 it's a disk, and the problem has been solved long time ago. And in dimension 3 this is the classical Kepler conjecture. And so, so now in each fixed dimension D we are interested in the maximal possible density. And we call this maximal possible density the sphere packing constant. And so here I avoid all the analytic details on how we define density, but that's I hope this is intuitively clear. And so we take somehow our configuration, and then we take big boxes and see which portion of their volume is filled by our non-intersecting balls, and then we have to go to a limit and, for example, take an upper or lower limit. So, so the sphere packing problem has been solved in a handful of dimensions. So, as I already told you, dimension 1 is trivial, and dimension 2 is not all that hard, even though formalizing the proof took quite some time. So the first argument on how to solve this problem was proposed by Axel II at the end of 19th century, beginning of 20th century. But then many mathematicians were somehow unsatisfied with the rigor of his proof. Of course, also at that time, mathematicians had a lot of discussions: what is a proof and how rigorous those should be. So eventually his proof was written by Laszlo Fejestoth, and so Laszlo Fejestoth also contributed a lot to this area by solving many similar geometric problems, and he also proposed a strategy for solving Kepler's conjecture. And so even though the strategy was somehow on a table, it was computationally very hard, and nobody really knew whether it will work or not in a reasonable time. And so then there is also a bit of a dramatic story around the proof of Kepler's conjecture, because there have been some announcements and then some gaps in the proofs were found. So so in 1998, Thomas Hales finally proved the Kepler's conjecture in dimension 3, and this is a beautiful result, but also quite involved. It contains a lot of computations, a lot of optimization, a lot of combinatorial computations. And so another interesting thing, it was maybe one of the first big results that were not only proven, but also formalized by some of the math formalization, one of the math formalization languages. And so and then my contribution to the field is the solution of the sphere packing problem in dimension 8 in 2016, and then in dimension 24 together with the collaborators. So together with Henry Kohn, Abhinav Kumar, Steven Miller, and Danila Radchenko, we have also solved the sphere packing problem in dimension 24. And so now maybe let me speak about this last two dimensions on this list, how we have done this. So here is the main tool we used for our proof. So unlike the solution of Kepler's conjecture, it turns out that in dimensions 8 and 24, we can solve the problem by using essentially Fourier analysis. So dimensions 8 and 24, for some reason, they are extremely nice. And here we don't need this very difficult combinatorial computations. We don't need to think too deeply on how spheres combine together. We can use this rather elegant tool from Fourier analysis. So methods like this, they are, at least in this geometric optimization problems, they have a name linear programming. And so here, this method works not only for sphere packing, it works for other geometric problems. And if I'm not wrong, I think so. In this concept, it was first worked out for binary codes, but then also adapted to other geometric optimization problems. So here, the idea is like this. So we need to construct an auxiliary function. And so in the case of sphere packing in Euclidean space, we would need to produce a Schwarz function. So the function which is infinitely smooth and also has fast decay, and all of its derivatives have fast decay. And this function needs to satisfy the following restrictions, the following inequalities. So first, there is a certain radius R0, which will depend on the density of the packings that we want to rule out. And so we want this function to be first, function itself has to be non-positive outside of a ball of radius R0. And then its Fourier transform needs to be non-negative. And we normalize our function by dilations, and so that the value of the function at 0 equals to the value of its Fourier transform at 0 equals to 1. And so you see, so here there is certain contradiction between conditions 1 and 2, because it's difficult for a function to be, on one hand, for a function to be negative, but then for its Fourier transform to be positive. So it means that we cannot take R0, which is very small. It's difficult to find functions. It becomes more and more difficult finding some functions when the R0 becomes smaller. And so whenever we can find such a function, then we can conclude that for each periodic configuration of centers of our perspective sphere packing in Euclidean space, if we know that the distance between these two centers is at least R0, then the configuration X has point density at most 1. And then, of course, this also gives us the bound on the sphere packing constant. So here maybe there are two steps. One of them is trivial, is how to translate this condition into a statement about sphere packing of balls with centers at points X and radius R0 divided by 2. And then another step, which is a bit more complicated, is to see that actually when if we have a bound which is true for all periodic configurations, and periodic it means that they are invariant with respect to shifts in some lattice, even though this lattice can be very big, very sparse, with very big fundamental domain. So that somehow if you know the supremum of the densities over all periodic configurations, then it also will be the same as supremum over densities of all possible configurations. And so this is a nice tool to prove upper bound on sphere packing density. And so the method was discovered by Kohn and Elkis, and then also by Gorbachev in the beginning of 2000s. And so Kohn and Elkis, they've applied this method numerically in dimensions from 1 to 36. And so this is what they have found. So here the blue line is the best known density. And so here you can see it as a continuous line, but this is, of course, actually, of course, the points so here on the blue line, they make sense only in integer dimensions. So I connected them by lines just for to be more, to be better visible. And the red line is the Kohn-Elkis Gorbachev upper bound. And so you can see that in most, on one hand, we can see that of course, the red line is above the blue line. And in most dimensions, there is quite a gap between the red line and the blue line. So what this means, that probably, of course, we don't know it from numerical computations, but we have quite a lot of confidence. I think in this regime, for small dimensions, we have quite a lot of confidence in both lines. And so it means that the method gives us an upper bound, but this bound is not sharp in most dimensions, with some exceptions. And so on this plot, we see that there is somehow a visible gap everywhere, and actually this gap grows, seems like it's growing for bigger dimensions. But then there are some special points, and those special points, which is hard to see on the plot, are actually dimensions 1 and 2, but also dimensions 8 and 24. So these are the points when two lines come very, very close together, at least numerically. And so Kohn and Elkis in 2003, they've proven the following theorem. So that the sphere packing constant in dimension 8 is at most 1.0016 times the density of the E8 lattice packing. And I will introduce E8 lattice in a moment. And in dimension 24, also the upper bound is very close to the density of an actual lattice, which is the Leach lattice in dimension 24. And so these were results from 2003, but then this similar computation was repeated later with better precision or for bigger dimensions, but yeah, but somehow like by the time I started working on this conjecture, I think, so these 3 zeros, they were replaced by like 60 zeros. So there was like 1 and then 60 zeros and then the density of E8 lattice and slightly worse result for the Leach lattice. And now I think, so like somehow experimentally is the number of zeros you can get here, it depends on how much you would like to invest into computation. And so of course this led to the conjecture made by Kohn and Elkis in their paper is that the linear programming bound is saturated, so it is sharp in this in the dimensions 8 and 24. So let me introduce to you about the special lattices where the magic happens. So this is the E8 lattice, and I think in this Congress we have already heard about this lattice several times in several contexts. For example, in the context of representation theory or mathematical physics. So this is E8 is an important object for example, as a Lie group and Lie algebra, and then E8 is its root system. However, this will not be very important for our conversation. What will be important for us to know its properties as a lattice in Euclidean space. And as a lattice in Euclidean space, it is an even lattice. It means that the length of every vector squared is an even number, and it's also a unimodular lattice, which means that its co-volume is 1. So we have, on average, we have 1 point of our lattice per unit of volume. And so it's from, actually, when it's a classical, we know that there exists exactly one lattice like this up to isomorphisms. And so again, like from the fact that lambda 8 is even, we would know that its shortest vector is at most square root of 2, and then by direct computation we can know that it exists, that indeed it has vectors of length square root of 2, and actually it has many vectors like this. It has this 240 vectors of this length, and also those vectors, they seem to be extremely nice. For example, they form the kissing configuration in dimension 8. So it means that we have, if we have, like here we have like one red sphere in dimension 8, then it can be surrounded by blue spheres of the same size, such that each blue sphere touches the red one, and blue spheres do not intersect. And actually, this is an old. This result goes back to 1970s, and it was again proved independently by Levenstein and by Adlishka and Sloan. So they proved that this is indeed the kissing number. So you cannot, like, 241 is impossible. And here the method of the proof, again, it's linear programming. And that's what we were able to prove. So I was able to prove that this also not only the shortest vectors somehow form this very nice local packing, but also globally E8 is the densest sphere packing in dimension 8. And then we also proved that working together with Kohn, Kumar, Miller, and Radchenko, we proved that E8 lattice has another nice property, which is called universal optimality. So it's somehow, maybe one can think of it as a relaxed version of the packing problem. So if we think of these points in a-dimensional space as interacting with repelling Gaussian potential, then the always E8 would be the optimal solution if you look at all configurations of the same density, of fixed density 1. And so E8 lattice is also, the Leech lattice is also a very important mathematical object. So this time it's not a root lattice, but it's also an even unimodular lattice in dimension 24. And in dimension 24, we know that we have actually 24 classes of isomorphism classes of such lattices. And of those 24 classes, there is only one where the shortest vector has length 2 and not square root of 2. So the Leech lattice is the only lattice where the first possible length is not realized. And of course, this makes it a good candidate for the sphere packing. So the Leech lattice was discovered quite late, and discovery actually came from coding theory, from engineering. So the Golly code was discovered by a Swiss engineer Golly, and then later Canadian mathematician Leech has constructed a Leech lattice based on his on this code. And again, shortest vectors of Leech lattice, they also form a kissing configuration, only this time much bigger. And again, the same method in the same paper where the kissing problem was solved in dimension 8, it was also solved in dimension 24, and again by the linear programming method. And so we would see that, so in this case, we can also consider a sphere packing associated to the Leech lattice, and this time it's nice because the lattice has density 1, so point density 1, but also here, because the shortest length is 2, we can also pack with balls of radius 1. So here we don't need to renormalize anything, because usually in the literature, we either choose radius 1 or we choose density 1, and then we have to always go back and forth and check the normalization. But here, both normalizations do coincide, which is maybe not terribly like deep mathematical fact, but a nice bonus. And so the E8 lattice also has this nice property of being universally optimal. And so how the proof goes, so now as we already have the Kohn-Elkis-Gorbachev linear programming bound, one thing we can do, so now there is only last piece of the puzzle has to be added, which is to construct this auxiliary function, which gives us not only the approximate bound, because for example, in the work of Kohn and Elkis, they would found approximate so they followed such functions which work not for square root of 2, but for slightly bigger number, and they would search, for example, for these auxiliary functions in a space of polynomial times the Gaussian. But of course, this way we would never get to, as we know, we would never get to square root of 2. And so the last piece was to find such a function which gives us exactly the sharp inequality here. And satisfies all of the three conditions. So this was my theorem from 2016, and then it's the same year, working together with Henry, Abhinav, Steven, and Danilo, we have constructed similar function for dimension 24. And so these two functions, f(E8) and f(Leach), they prove sharp bounds for the sphere packing problem. And so here the name is it was suggested by Stephen Miller to call those functions magic functions because they somehow do the work for us, spare us a lot of work. And so this is how the function looks like. So here's the plot of the function which corresponds to the magic function for the E8 lattice. And so here it's, because this is a Schwarz function, so it decays very fast. So here I multiplied it by this, I would say, rather randomly chosen fast-growing function, so that we can just see the behavior of the function long enough. Without this factor, it would just have a bump here and then being almost zero here. So then I would not be able to show you the nice features of the function. And you can see what the nice features of this function is that, of course, both functions do satisfy the Kohn-Elkis conditions. But then, maybe what I would like to drive your attention to is that they satisfy it, but they also have many zeros. So there are many points where somehow the condition is almost failed. So to say so. And so, of course, you can see also that the zeros of the function, double zeros of the function f and the double zeros of its Fourier transform are exactly at the lenses of the vectors of the Leach lattice. So here the lenses are squared, again, to get a more beautiful picture. And of course, this fact, these double zeros, they have, there is an explanation to this. So this is something what follows from Kohn-Elkis condition and the existence of the E8 lattice in this case. And so, okay, so now the question is how to find these functions. So first, important step is to maybe simplify our problem, and instead of searching for magic functions in the space of this functions of 8-dimensional variable, to search for functions which are radial, so where the value of the function depends only on the distance to the origin. And so why is it a good somehow good assumption? Because if we have any function that satisfies the Kohn-Elkis condition, we can take this function and then average it over all the rotations. And the conditions of the Kohn-Elkis, so the Kohn-Elkis condition, they are invariant with respect to rotation around the origin. So if we have one function that satisfies the conditions and any of its rotations, would also satisfy the conditions. So we can just average over all the rotations, and then we obtain a radial function. Searching for a function of one variable is much easier than searching for a function of 8 variables or 24 variables. And so another clue to find the magic functions are, again, this double zeros. So first, let's see why those zeros are inevitable. And so this comes again from, so this can be explained from what is known complementary slackness in complex optimization. Or another way to see it is that we can have so in both cases, our optimal solutions are lattices, so we can use the Poisson summation formula and, for example, apply it to our magic function. And so then, because it satisfies the Konelkis conditions, we will have such a chain of inequalities. And as we have started with one and finished with one, so that's why we see that these inequalities here, they actually have to be the equalities. And the only way they can be the equalities if all, if this condition is satisfied, if the values of f and the values of its Fourier transform are 0 for all non-zero elements of the lattice. And also, of course, here we also implicitly use the fact that our both of our optimal solutions, they're self-dual, so the lattice, E8 lattice or Leach lattice, is equal to its dual. Yeah, so, but now it turns out that these two conditions, they're actually sufficient to recover our function uniquely if you also make one extra assumption, and this extra assumption would be that our the magic function has to be a Schwarz function. And for example, in the original method of Konelkis, and I think the same for Gorbachev, they did not consider Schwarz function. They considered a wider class of functions. So what I wrote on my slide where I cited their theorem, actually wrote a slightly weaker theorem, because their method allows for more general auxiliary functions. Okay, so now so here what I will give you, I will give you the recipe how to produce the function. And even though I think I did not include it in my slides for today's talk for the sake of time, so maybe even in the question session I can go deeper into that. But with our later work on universal optimality, so in 2016 we have just constructed the function. We gave the construction and proved that they satisfy the conditions of Konelkis linear programming. And later we have proven that actually in the class of Schwarz functions, these solutions are unique. And so today let me just give you the construction, how it works for us. So because we have these double zeros, what I would like to do, I would like to search for my magic function in this form. So first this sine of p over r squared over 2, and here r is the length of my vector in Euclidean space. So I include the sine squared to create all these double zeros. And then I will have some other factor here. And so this factor, I will just, out of blue at this point, I would like to search for it in such a form. I would like to search for it as an integral of a certain holomorphic, counter-integral of a certain holomorphic function at the upper half plane. And later I will tell you that this is not any function. This function has to satisfy very particular transformation properties. And so yes, maybe so this is something which actually this is a Laplace, in some sense this is a Laplace transform of this function. And so yes, what we want from our function phi here is that it would have certain nice transformation properties with respect to the action of SL to Z on the upper half plane. And yeah, so as you remember that for function f itself, it has double zeros everywhere except for the first zero. So it means that in the first, how can this happen? So what we can do, we will search for this function so that the integral converges absolutely for r bigger than this smallest vector, and then can be analytically continued to other values of R, or I would say continued in a certain way. So now, what are the properties we have for this function? So here comes the trick, which later I called the chicken claw contour trick. And so we know. So now we would like to compute the Fourier transform of this function. And our goal is, so now our function has double zeros because of this sign here. And the goal is to compute the Fourier transform of this function. And I want, because I want this Fourier transform to be easily computed, and this is actually the secret reason why I've chosen my integral representation in this form. Because in this form, it would be easy to compute the Fourier transform of f. But now I want to make some manipulations with this Fourier transform and to somehow to create the sine squared again. And so here I'm rewriting my function in such a way. And now I can apply the Fourier transform. So in the Fourier transform, it's easy, I just apply it to this Gaussian. And so here I can make this change of variables. And again, this is somehow, while representation is working in the background, it helps, it translates the Fourier transform, which acts on Schwarz functions, into an action of this transformation at the upper half plane. And so here, with some computations, I can actually see what are the desired properties, what are the desired transformation properties for the function phi. So maybe I will jump over this. Probably I will not explain every step here, but these are some usual computations with the integrals, and so we would get this type of representation for the Fourier transform of our magic function. And so at the end, because we do want to get the sine squared here, and then these conditions in red, they would be sufficient for us. And so now it turns out that actually these functional equations, they can be solved can be solved explicitly, and the functions we use to solve them, they would be modular forms for of level at most 2, and quasi-modular forms. So if you take a combination of those, we will find a function which satisfies all these conditions. And also another important thing here is that we also have restrictions on each of these functions near the cusps of, somehow at the ends of our intervals, we require either vanishing or certain asymptotic behavior. And so it turns out that those conditions can be solved, and they can be solved uniquely. And so this was somehow the original proof, the original method, and then only after we have written a second paper on the universal optimality, then we could understand how the function is actually constructed. And so after we have constructed such a function, such a candidate on a magic function, we still have to prove that it is magic, because as you remember, for now our guiding principle for constructing f was to satisfying this double zeros condition. But double zeros are not enough to satisfy the Kohn-Elkes theorem. For Kohn-Elkes theorem, what we need also to verify the inequalities. So the final step would be to verify that this function satisfies the inequalities of Kohn-Elkes-Gorbachev theorem. And so this is this final step. Initially, we have done it by some numerical computation, but now there have been a development, and actually 2 people independently have found 2 different analytic proofs for the necessary inequalities. So one is Dan Romnik, and another one is Shivu Li. And so now let me tell you a bit more what happened after the proof of the theorem. So yeah, so one of course question that still exists from this, one can ask by looking on the graph of comparing the linear programming bound to the known densities of packing in various dimensions is, so in which cases can we hope for this linear programming bound to be sharp? And so here, one thing that I think the original method was suggested by Henry Cohn and his collaborator was to somehow to search for abstractions to linear programming. So actually, linear programming is not a perfect method, and sometimes it cannot be sharp if you know that there is an abstraction for. So abstraction, well, maybe one can think a bit of a sort of something like a fake packing, something that looks like a Poisson summation formula, which comes from a packing, but in fact it's not. It is not that. And so here is the following statement. So let lambda n and lambda n tilde be two sequences of positive real numbers, such that this Poisson-like summation formula holds. And so if you can see, for example, if we have a lattice, of course, for each lattice, we would have a Poisson summation formula like this. But, and so if we have if we have a formula like this, then we would know that the alpha, the linear programming bound cannot be better than alpha 1. Because for the linear programming bound, we could think of this object also as a packing. And so here the situation, like most general situation, would be like this. So we would have some real value of the sphere packing problem, which we either know, like in dimensions 1, or don't know yet. And there could be a linear programming bound, which usually, of course, for the linear programming bound, we can compute it with very high accuracy, but still when we have we never really know how far away it is from the actual best possible linear programming bound, or almost never know. And then there might be upper bounds on the sphere packing problem obtained by other methods, for example, semi-definite programming or any other method you can think about. And so if we have a situation like this, that we, on one hand, we have, if the alpha 1 is, we could find such a Poisson-like summation formula, and alpha 1 is here, but then another upper bound on the sphere packing problem is here, then we would know that linear programming is not sharp in this dimension. And of course, in some rare cases, all these 4 points, they can actually come together. And so we have seen two cases when all 4 points come together, but then the question is, well, what about other dimensions? And so, yeah, so for now, we know that in this, at least in these dimensions, in dimension 3, 4, 5, well, 6, 12, and 16, the sphere packing problem cannot be solved by the linear programming method. So here, the first paper in this method, it was so Henry Cohn and Nick Triatanfilou. I apologize if I don't pronounce the last name correctly. They came up with this idea, and they were constructing the Poisson-like formulas from modular forms. And then young, I think at that time, PhD student, Rupert Lee, he came up with a different alternative method for constructing such Poisson-like formulas. He would construct them from periodic functions on somehow small, not small, but like lattices with a small step in Euclidean space. And his method turned out to be very effective for small dimensions. So he could actually prove, for example, dimension 3, the sphere packing problem in dimension 3 cannot be solved by linear programming method. And of course, this was something we already believed in, but he actually showed that yes, sphere packing, so that here linear programming itself cannot be sufficient. And of course, then there is a interesting theoretical question: are there any other dimensions except for 1, 2, 8, and 24 where the LP bound is sharp? And so, okay, so now let me speak a little bit about other. Yes, maybe first I'll just jump. So let me now speak a little bit about other applications of this linear programming method. So it turns out that it's useful not only for packing problems, but it works in other related problems in physics and in quantum error correction. So first, let me speak about this result. So the connection between sphere packing and quantum gravity. And here the story is interesting because the work of Hartmann, Matzak, and Rastelli, I think they did their work. So the initial result on this modular bootstrap. It was done in 2016. Only our paper was published, mathematical paper on sphere packing was published in spring and appeared in archive in spring, and their result appeared in the fall. But I think they actually did the work independently. And so what they found, they used what is called the modular bootstrap for understanding the spectra of the conformal field theories. And so I do not claim that I know what are conformal field theories or could explain it here, but it is so the way I think of it, it is as a certain analog of this optimization problem. So of course, conformal field theories, they can be stated mathematically, and then so then they have certain rules that work in it, and they have a spectrum. And so the question is what this spectrum could be. And so it turns out that finding constraints for this spectrum, it becomes, in a certain sense, similar to constraining, for example, spectra of manifolds with certain conditions, or to, for example, searching for or spectra of possible lenses of vectors in lattices. And yeah, so here there is a method called modular bootstrap, which is somehow, in fact, very similar to the Kohn-Elkes-Gorbachev linear. Only that the terminology is different. So here are some technical details. So this modular bootstrap can be applied to this particular algebra, U1C, where C is the central charge, and so the correspondence here is that the dimension is twice the central charge. And then on the mathematical level, actually, this modular bootstrap, it becomes essentially the same as Kohn-Elkes linear programming bound. Maybe with one difference is that it looks not at the it looks at the functions which are eigenvalues of the Fourier transform with eigenvalue -1. So what the physicists have done, they have found half of the magic function, so the -1 Fourier transform part of it. And then it turns out to prove the optimality of some spectra of such conformal field theories. And so here is another connection that I have recently learned about from a colleague who is now in EPFL. So this is the application of this version of quantum Kohn-Elkes bound for quantum error detecting codes. And so here the problem is the following. So it has some similarities with the linear programming bound for the sphere packing, but also, it's also different in some sense. So here the idea is that we need to find again this auxiliary function, and I think we also can be quite flexible on the class in which it lives, but Schwarz functions definitely work. And so then, but then here, instead of optimizing the ratio of the function to its Fourier transform, here we are looking at the supremum of this value of the whole interval from 0 to d. And then it turns out that the magic functions which work for the sphere packings, so certain easy modification of them also gives a bound here, which proves optimality of certain quantum error correcting codes in dimensions 8 and 24. And yeah, so together with Asghar, we plan to run a seminar next fall, and then I will probably learn what this words actually mean. And so maybe now, as my lecture comes to the end, maybe I would like to say a few words about one of my favorite questions in the whole sphere packing. In the sphere packing problem, it is how to understand the sphere packing problem for very, very big dimensions. And so what do we already know? So we do know that the sphere packing constant, it decays exponentially as dimension goes to infinity, and the question is at which rate does it decay? And here's somehow, okay, we have a very easy lower bound, which is tells us that any saturated packing has density at least 2 to the minus d. And saturated means that we have a configuration of balls such that we cannot add any more balls in there. So it's configuration such that if we add one more ball with any center, it will necessarily intersect one of the existing ones. And then it's a very easy geometric argument to say that if we have such a saturated configuration, its density has to be at least 2 to the minus d. And yeah, and then there is also an upper bound, which is a Kabatanski-Levenstein bound. And it tells us that the sphere packing constant has to decay at least like this number, so it's like 2 to this exponent. And also the upper bound is quite old by now, but no exponential improvements. There have been some improvements, but no exponential improvement since 1978. And so, but remember, maybe now let me tell a little bit more. So in this bound, it seems to be very difficult. Not much progress has been made. But let me tell you a little bit about the progress on this side, because I think this is a story that gives me a lot of optimism. And the first, maybe just as for a moment, I would introduce some new notation, which is, let's look instead of all sphere packings, we can look only at the lattice packings. And so then we can introduce a lattice sphere packing problem as a best density of the lattice packing. And we will normalize it in this way. So we already know that 2 to the minus d is somehow with a very natural normalization. And so, let's normalize our lattice packing constant like this, and then the exact values of the lattice sphere packing constant are also known in a few dimensions. The here list is a bit bigger than for the general packing problem. So here all dimensions up to 8 are included, and also 24. And it turns out that 9 is actually a very difficult computational problem people in the field are working on, but still can somehow, even though this is the lattice packing problem in a given dimension such as 8, it would be essentially a finite, at least finite dimensional problem, but this finite dimension is still very big, and so I still have not heard that somebody cracked the 9-dimensional problem here. And so this is somehow the history on how the lower bounds on the lattice packing problem improved. And yeah, so here you can see that comparing to this naive bound, the density of the saturated packing, all the improvement, so we don't have exponential improvement here. We only have something which is polynomial or even linear in n. And so, of course, so Minkowski, actually, okay, so here maybe it's a bit not true. So Minkowski improved this constant to 2. So for lattices, we can replace 1 by 2. And then then Rogers worked on this problem, and he wrote many papers on it, but eventually could add this linear factor, d. And then for a very long time, there was improvement on the constant factor before the linear factor. So here I don't include every improvement that have happened on the constant, but maybe some ideas that I like. So there was a paper of Ball, and then an interesting idea by Stephanie Vance, who suggested to use symmetries to prove the existence of good lattice packings. And then the idea of Stephanie Vance was really pushed further by Akshay Venkatesh. And so Venkatesh suggested considering lattices with a symmetry of cyclotomic field, and he could prove such a bound not for all dimensions, but for the most sparse sequence of dimensions. He could add this log d factor. And now actually something quite unexpected happened 2 years ago when a group of combinatorists were able to improve this lower bound on the sphere packing constant by a log factor. And so their method is combinatorial. It works in any dimension, does not use any special structure. So essentially, this is somehow a statement about random packings if we analyze them very, very carefully. And yes, I think this result made a lot of splash. And this year, something else have happened, also very nice. So now, for 2 years, somehow, at least in terms of lower dimensions, so unrestricted sphere packings, they were winning over lattice packings. But this year, everything has changed. And Boas Klartak proved this new theorem where he was able to include the n-square factor for lattice packings. And yeah, so his proof is also probabilistic, so it somehow only explores this the space of lattice packings in a smart way. So, and it turns out that we can get n squared here. So maybe I could just tell you that somehow the speed at which the lower bounds accelerate give me somehow hope, and that exciting things happen in our time. So maybe at this point I will finish my talk, and I'm ready to answer your questions.
Thank you for the wonderful talk. Any questions?
Thank you very much for wonderful talk. I actually have 2 related questions. So the first is, do you believe the answer for lattice packing and not lattice packing would be different once we know there is good reason to believe the lattice packings should always be the answer? And the second is where you think the density will go, right? Would be close to 2 to the minus n, or we eventually should improve exponentially?
Yes, so of course I don't. It's very hard to betting on this. I can tell you what I would find. I do believe that unrestricted packings, they should, big dimensions, should be better than lattice packings. Just because why not? I think that we have better results for lattice packings just because we understand them much better. And also, I do hope that correct answer is like an exponential rate somewhere between Kapetansky-Levenstein and 2 to the minus d. Somehow, I know there is a school of thought where people believe that 2 to the minus d up to something smaller, like exponentially speaking, 2 to the minus d is the correct answer. I hope that not. So I think that people who work on lower bounds believe in this, and maybe the situation is like this. Is of course like 2 to the minus d is what happens probabilistically, what like random thing or something reasonably close to a random thing is 2 to the minus d. But at the same time, I do hope that there is maybe some insane algebraic construction which gives something better.
Right, so do you believe that this Kohn and LK's linear programming upper bound can detect like the optimal growth at infinity?
Sorry?
Do you believe this linear programming bound can detect the optimal decay at infinity?
So optimal comparing to what? To
No, so there are a couple of lower bounds, and you said there is no progress on upper bounds, right?
okay, sorry. Okay.
Like, as in, we know, like for large dimensions, it's very hard to use their method to get anything optimal, but maybe they detect them.
Here again, there are several schools of thought on that, and I think there is a I think Torquato, he made this kind of, I don't know, maybe like a conjecture that linear programming is actually close to the truth, and this is like the main abstraction, and everything else is a detail. I don't know how much actual proof we have about that, because I think it's just when you try to, this is another again phenomenon, if you try to improve on so nobody, at the moment, nobody was able to improve on this linear programming asymptotically. So usually we can do it in particular dimensions, but then it also becomes computationally costly. And but at the same time, why could not we do it? Is it because it's impossible, or just because we have not found the right idea yet? So I really hope that maybe we have not found the right idea yet. But yeah, but who knows? Here I would not. I would say probably we don't know enough to answer that question. At the same time, somehow it's nice to think that okay, we have to just figure out what this mutual like distances between distances between points should be on average, and from this we should be able, for some reason, to reconstruct the configuration. But okay, so that would be nice, but I don't see why that should be true.
Thank you.
Thank you for a beautiful talk. I have a maybe naive question. This is a beautiful field. All these results are for Euclidean geometry. So is it meaningful or interesting to consider the same problem, but if you change the metric space?
Yeah, of course. The method is very flexible, and it has been used in other metric spaces as well. So I think the original method is the method of Delsart, which comes from codes over finite alphabets. And then in principle, it can be applied to other spaces. And the method works the best when the space has some symmetries, because then this somehow reduces the dimension of where our auxiliary functions are defined. So in principle, yeah, it's very flexible in that sense.
Anybody looked at this in a serious way?
Yes. So people looked at this in, as for example, this is how the optimality of Golay code and Hemming code was proven. And I think those results were obtained even earlier than the results for Euclidean space. And I know the groups who work on this. Of course, another interesting thing that I think many mathematicians work on is the sphere, because it's a nice mathematical problem. But then also there are results in hyperbolic geometry. And in hyperbolic geometry, it's a bit more complicated because Fourier analysis there is a bit more complicated. But methods do work. Maybe it's what is not so easy is to get sharp results, because somehow it seems like nature gives us those in short supply, but also we have to be smart to find them. And yeah, but I think in hyperbolic geometry there is a couple of problems where people do believe that sharp results should be possible. Only, to my knowledge, nobody have done it yet. So.
Thank you.
I did ask her beforehand to get